From ancient bronze gear predicting eclipses to qubits cooled near absolute zero, this is the 2000-year journey of computers in just minutes. Ancient foundations. The Antikythera mechanism, built around 100 BCE, is the world's first known analog computer. It gears calculated eclipses and planetary cycles with astonishing accuracy. Mechanical dreams. In 1830s, Charles Babbage designed the analytical engine, a mechanical general-purpose computer. It had a store for memory, a mill for calculation, and a pinch cards for programs. Ada Lovelace even wrote the first algorithm for it. Electronic beginning. Fast forward a century, ENIAC completed in 1945 filled an entire room with 18,000 vacuum tubes. It could calculate 1,000 times faster than any mechanical computer, but reprogramming it meant rewiring cables by hand. The transistor revolution. In 1947, Bell Labs invented transistors smaller, faster, and cooler than vacuum tubes. This single invention made modern computers possible, from pocket calculators to smartphone. The microprocessor. In 1971, Intel released 4004, the first commercial microprocessor. For the first time, an entire CPU fit on one chip. It powered calculators, but it opened the door to the PC revolution. Morey's and Dennard's scaling. In 1965, Gordon Morey predicted that the number of transistors on a chip would be double every 2 years. Dennard scaling explained why shrinking transistors kept power constant. But by the transistors in mid 2000s, physics caught up. Power leakage. Ended scaling pushes us into the multi-core era. Today's silicon. Today's computers thrive on parallelism. GPU, AI accelerators, and chiplets push performance forward, not by faster clock, but by doing more at once. Quantum basics. Now computing enters in a new frontier, quantum. Unlike bits and which are 0 or 1, qubits can exist in superposition, both states at once. Entanglement links qubits so that measuring one instantly influence the other. Together, these effects allow new types of supercomputation, especially in chemistry, optimization, and cryptography. The hard part, error correction. But quantum computers are fragile. Noise and errors overwhelm unless we use error correction by combining many physical qubits into single logical qubit and operating below a threshold error rate. Systems can scale reliably in 2024 and 5. Labs like Google and IBM demonstrated exactly that error rates improving as system grew. From the bronze gear to qubits cooled near absolute zero, computers have been a story of shrinking, scaling, and rewriting the rules. The next chapter, hybrid systems, where classical supercomputers and quantum processors work together. The journey of computing isn't over, it's accelerating.